Today we will discuss about brilliant zones. A brilliant zone can be defined as a Wegener-Seitz primitive cell in reciprocal lattice. You know what is Wegener-Seitz cells? So a Wegener-Seitz cell in reciprocal lattice is defined as or is called as a brilliant zone. So in the evolved construction which we have seen in our previous section, that all the k values for which the reciprocal lattice points intersect the evolved sphere are Bragg reflected. So a brilliant zone is the locus of all those k values in the reciprocal lattice which are Bragg reflected. So we have seen the evolved construction, and all the points on the sphere for all the k values for which the reciprocal lattice intersects the evolved sphere are Bragg reflected. So a brilliant zone is the locus of all those k values as the reciprocal lattice, which in the reciprocal lattice which are Bragg reflected. Now we will construct the brilliant zones for simple cubic structures, simple square lattice, BCC lattice and FCC lattice. So first we will construct the brilliant zone for simple square lattice of side A. The primitive translation vectors for this lattice are, that is simple square lattice, can be given by A is equal to A I cap and B is equal to A j cap. So we are considering a simple square lattice. So the primitive translation vectors are given by these vectors A and B, and the corresponding translation vectors of the reciprocal lattice, which we have discussed in our previous class, which can be given by S star is equal to 2 pi by A I cap and B star is equal to 2 pi by A j cap. Therefore, the reciprocal lattice vector is written as G vector, which is equal to 2 pi by A H I cap plus K j cap. This we will obtain from the definition of the reciprocal lattice, where we have defined the reciprocal lattice vectors, where H and K are integers. The wave vector K can be represented, the wave vector is usually represented by K is equal to Kxik plus Kyj cap, since this is in xy plane. So the Bragg's condition is given by 2k dot g plus g square is equal to 0. So using these two vectors, g vector and k vector, the Bragg's condition can be written as 2 times k dot g. 2 times k dot g means this vector into this vector, dot product of these two vectors plus g square. G square means this vector square. So we can written this equation like this, and this will give you a value. So in this equation we can take one term right side to this 0, and so minus sign will appear here, and also 4 and 4 will cancel and 1 pi will cancel, pi by a will cancel, so the remaining will be minus pi by a into h square plus k square on the right side, and on the left side I dot I, so which will give you k x into h plus ky k. So these two terms will remain from the Bragg's condition. The k values which are Bragg's reflected are obtained by considering all possible combination of h and k. So the Bragg's reflected k values are obtained by the possible combinations of all these h and k. So what we are doing is, for h is equal to plus or minus 1 and k is equal to 0, that means h is equal to plus or minus 1. H is equal to plus or minus 1 and k is equal to 0. So k is equal to 0 means this term is 0. And so this term also will be 0 since this is k. So what we will get, hx is equal to minus pi by a h square, where h is equal to plus or minus 1. So that kx will give you value plus or minus pi by a. And ky is arbitrary in this case. Also for h is equal to 0. So the first case we have taken k is equal to 0. Now we are taking h is equal to 0 and k is equal to plus or minus 1. So this term and this term will go, and in that case we will obtain from this equation ky is equal to plus or minus pi by a, and in that case kx is arbitrary. So the four lines, that is kx is equal to plus or minus pi by. So we have got four equations. Kx is equal to plus pi by a and minus pi by a, and ky is equal to plus pi by a and minus pi. So four equations corresponding to this kx and ky. So these lines can be drawn these lines can be drawn as in figure. I have redrawn this picture in another paper and I will show you how it is. So here I have redrawn this. So this is kx axis and this is ky axis. So I have marked here on the x-axis pi by a, 2 pi by a on the positive side, and minus pi by a, minus 2 by a on the left side. Similarly here positive values on the upside and negative values on the downside. And kx is equal to pi by a means this point. So a line passing through this point will represent kx is equal to pi by a. So this is the line representing pi by a, and here this is the value corresponding to kx is equal to minus pi by a. So the line passing through this point represents kx is equal to minus pi by a. Similarly, this point represents ky is equal to minus pi by a, and this point represents ky is equal to pi by a. So this line is ky is equal to pi by a, this line is ky is equal to minus pi by a. So this is the boundary defined by these four lines, these k values. These four k values define a boundary which I have shaded with a crossed lines. So this is known as the first Brillouin zone corresponding to this square lattice. Okay, so this is the figure. Here this is kx. These are the four lines 1, 2, 3 and 4, and the middle portion which is bounded by this four line is representing the first Brillouin zone. Okay, first Brillouin zone of the square lattice, and which will have a side equal to length 2 pi by a, because this from the middle to this portion this length is pi by a, and here it is also pi by a. Similarly, this length is pi by a and this length is pi by a, so the total length is 2 pi by a. So this is the first Brillouin of the square lattice of having side length equal to 2 pi by a. In addition to this, a set of lines some others are also possible which satisfy the first previous equation. For example, h is equal to plus or minus 1 and k is equal to plus or minus 1. The above equation gives the following set of four lines. So this is our equation. So what we are doing here is h is equal to plus or minus 1 and k is equal to plus or minus 1. So from this equation what we will get, this is plus or minus 1 kx, and here plus or minus 1 ky, and here plus or minus 1 square plus or minus 1, which will give you 2, and it will give you a value 2 pi by a. Okay, so our equation is from these values plus kx plus or minus kx plus or minus ky is equal to 2 by a. So we will get 4 equations from this expression. Okay, that is this 4 from this expression, 4 equation we will get, that is kx is equal to plus ky, which is equal to 2 pi by a, and kx positive with ky negative, and the third one is minus kx plus ky and minus kx minus ky. So these are the 4 equations. So these 4 equation will represent 4 line in the graph. So we can mark these equations on this graph. So first equation, if you are taking the explain you the second and third equation. Look at this equation. From this we will get kx is equal to ky plus 2 pi by, and this is ky is equal to kx plus 2 pi by. So this is the line representing ky. Okay, so ky plus 2 pi by a means ky plus 2 pi by a means this point. Similarly, the third equation, kx plus 2 pi by a means kx is this line, plus 2 pi by a means this point. Okay, similarly minus ky plus 2 pi by a, and the first and fourth equation can be represented by this point and this point. So what will be the lines? Okay, lines as I have drawn these lines here, or I can draw it here itself. So this will be so first we have got a square lattice touching this. So this was the first Brillouin zone, and now the area covered by the second set of lines will represent the second Brillouin zone. So this is the second Brillouin. So the additional area bounded by these 4 lines, which we have just shown from the figure, is the second Brillouin zone. I have shown it shaded. So the parallel lines, the horizontal lined area represents the first Brillouin zone, and the additional area, which is represented by vertical lines shaded, will give you the second Brillouin zone. Okay, the boundaries of the Brillouin zone. Brillouin zones represents a locus of the k values that are Bragg reflected, and hence may be considered as the reflecting planes. The boundaries of the first zone represents the reflecting planes for the first order reflection, and those of the second zone represents the reflecting planes for the second order reflection, and so on. A k vector that does not terminate at a zone boundary cannot produce a Bragg reflection. So the k vector should be terminated at the zone boundary, otherwise it won't Bragg reflected. Thus the Brillouin zone pattern can be employed to determine the X-ray diffraction pattern of the crystal structure and vice versa. So the Brillouin zone pattern will give you the X-ray diffraction pattern, and hence pattern of the crystal structure. Okay, So this is the importance of Brillouin zone in reciprocal lattices. And the Brillouin zone for a three-dimensional cubical lattice is constructed using the generalized equation. So instead of two lattice parameter, third parameter will appear, hkx plus ky plus lkz. In the case of three-dimensional cubic lattice, we have just discussed the square lattice. So here three terms will be here, h square plus k square plus l square, where a is the length of the cube edge. It is clear from this equation that the first zone is a cube having side equal to 2 pi by a. The second zone is formed by adding pyramids to each face of the cube, that is of the first zone, as triangles are added to the square in 2 dimensions and so on. So that is, we have seen here the first one is square, and the second zone is constructed by adding pyramid to the face of this square, like this face of this square. That's what we said here, described here. So there is another simple method to determine the Brillouin zone. From the previous figure, there is reciprocal lattice vector G, which satisfies equation, that is the Bragg's condition, to k dot G plus G square is equal to 0, is a perpendicular bisector of the zone boundary, and all the k vectors lying on this boundary have the same G for reflection. Thus, it is sufficient to consider only the allowed G values and their normal bisectors to construct the Brillouin zone. The first Brillouin zone is the region bounded by the normal bisectors of the shortest possible G vectors. The second zone is the region bounded by the normal bisectors of the next larger G vectors, and so on. This method is used to determine the Brillouin zone of a BCC and FCC lattices. This is not nothing new. This is just what we have used in the construction of Wegener seed cells in usual primitive lattice crystal lattices. So what we are doing in primitive lattice is that for constructing a Wegener seed cell, we are considering a lattice having lattice points like this, and what we will do is we will choose a point and we will draw vectors to nearest neighbors in all possible directions, okay, and so on. And what we will do is and we will do perpendicular bisectors to all these vectors, okay, and perpendicular bisectors to all these vectors, and the boundary bounded by these will give you the Brillouin zone. Okay, so first we will draw neighbors, vectors to the nearest neighbors, and for the second Brillouin zone we will draw vectors to the next nearest neighbors, and so on. So this is what we are doing in this for Brillouin zone in reciprocal lattices also. This is how we are constructing Brillouin zones in simple in reciprocal lattices. Now next we will discuss the Brillouin zone of BCC lattice, body-centered cubic lattice. So the body-centered cubic lattice, the primitive translation vectors of BCC lattices are given by A, B, C, which we have seen in our previous class, and the corresponding reciprocal lattices are A star, B star, and C star. We have constructed this reciprocal lattice in our last classes. so I need not explain this again. Now the G type reciprocal lattice vector, which can be represented by HA star plus KB star plus LC star, which can be given by 2 pi by A times. So what we are doing is we are writing here the A vector, which is 2 pi by A is common in all three vectors, so we can keep this outside the bracket, and I plus J first term and J plus K and K plus L in the K plus I in the last terms. And what we are doing is that step I have not shown here, and in the next step what we are doing is we are combining the terms containing I. So here it is I H plus L, and in the next term H plus K, and next one K plus L, etc. Okay, so that's what we have done here. And the shortest zone G, shortest non-zero G's are the following 12 vectors. 2 pi by A plus or minus I plus or minus J, and 2 pi by A plus or minus J plus or minus K. So from these vectors, so the shortest non-zero G vectors are given by these expressions. Okay, so the first Brillouin zone is the region enclosed by the normal bisector planes to these 12 vectors. From this the first Brillouin zone is the region enclosed by the normal bisectors of these planes. So from this we will get 4 plane from this, 4, 4, 4. So 12 planes. So this first Brillouin zone are the normal bisectors to this plane. This zone has the shape of a rectangular 12 faced solid. So which will have 12 faces and which will be rectangular in shape. Okay, represented by this 12 planes. And this is about the Brillouin zone for BCC lattice. So what we have done, I will summarize. We have written the primitive translation vectors for BCC lattice and the reciprocal vectors corresponding to this BCC, and we will write down the G vector in a reciprocal lattice, and from this we will find out the possible shortest G vectors, and the intersection of these 12 vectors will give you the Brillouin zone. Okay, first Brillouin zone, which will be, since this vectors having 12 vectors or 12 lines, the first Brillouin zone will have 12 faces. Okay, so this is about Brillouin zone of BCC lattice. Now the Brillouin zone of FCC lattice, face-centered cubic lattice. So the procedure is same. So what we have to do is we will write down the primitive translation vectors of FCC lattice, which we have seen in the previous class. So these are A, B and C, and the primitive translation vectors corresponding to this in the reciprocal lattice can be which we have derived or constructed in the last section, which are A star, B star and C star, which will be given by this. Okay, and the corresponding G type vector is defined from the equation HA star plus KB star plus LC star, which from this expression we will get 2 pi by A and outside the bracket and inside these two bracket, which we will get from this previous equation. And from this the shortest non-zero G's are the following 8 vectors, that is 2 pi by A plus or minus I plus or minus J plus or minus K. Okay, and the boundaries of the first Brillouin zone are determined mostly by the normal bisector planes to these above 8 vectors. However, the corners of the octahedron obtained in this manner are truncated by the planes which are normal bisectors to the following reciprocal lattice vectors, which are 2 pi by a plus or minus 2i, 2 pi by a plus or minus 2j, 2 pi by a plus or minus 2k. So we will get the boundaries enclosed by these 8 vectors, and the normal to these bisectors are truncated by the planes which are normal bisectors to the following 6 reciprocal lattice vectors. So we will get this is how we construct the Brillouin zone for FCC lattice. Okay, so if you want, you may write down these vectors in a notes, and you can construct these vectors and how this will appear. Okay, so these are about the Brillouin zones for FCC, BCC and simple, square and cubic crystal structure.